My name is Kareem Khalifa, and today we'll be translating with quantifiers. Today we'll break our talk into three separate sections. The first is a discussion of the Aristotelian forms. Next, we'll talk about some nuances in translating complex noun phrases. And finally, we'll look at vacuous universal statements and context. For those of you who don't know, Aristotle was an ancient Greek philosopher who lived in the 3rd century BC. He wrote on pretty much everything, including logic. Today, we'll look at his nice classification of 4 basic kinds of quantified statements. First, they're just plain old universal statements. These have the form of all P's are Q's. For instance, all men are mortal. Recall from our previous lecture that we translate the verb to be in universal statements with the arrow, that is a conditional. So using modern formalization techniques, much later than Aristotle, we would translate that this way. For all x, if x is a P, then x is a Q. The next statement that we'll look at are simple existential statements. These have the form of some P's or Q's. So for instance, some men are jerks would be an example of this. Recall from the previous lecture that when we have the verb to be in an existential statement, we translate it as and. Thus, for statements of this form, we say that there exists an x such that x is a P and x is a Q. The third kind of quantified statement that Aristotle discusses is of the form no P's are Q's. For example, no men are protozoa. Now, there's 2 ways of translating this. Here's perhaps the more literal version of this, which is there does not exist an x that is both a P and a Q. Right? This says there's literally no thing that is both a P and a Q, which pretty closely mirrors the English. However, another way that you could translate this is for all x, if x is a P, then x is not a Q. This says all P's are non-Q's. So for example, all men are non-protozoa. It's worth noting that these 2 statements in first-order logic are equivalent to each other. We'll be able to prove that in a little bit. The fourth and final Aristotelian form is some P's are not Q's. For instance, some philosophers are not jerks. This is a pretty literal translation given what we've seen before. What we say is there exists an x such that x is a P and x is not a Q. Okay, let's turn to complex noun phrases. These are where you don't just have a simple P is a Q or something like that, but you end up having multiple adjectives that you're using to modify your noun. For example, let's take the sentence, a nasty goblin is armed and dangerous. Right? Here the complex noun phrase is nasty goblin. We actually also have a complex predicate because we don't just have armed or just dangerous, we have armed and dangerous. Furthermore, this is what we call an existential noun phrase. This is just talking about there being at least one goblin, but not necessarily making a statement about all goblins. This is going to come as a big surprise. When you have an existential noun phrase, you use an existential quantifier. And what we know about existential quantifiers is that ands are basically what are running the show. That's what we see here. Basically what we're saying is there exists an x such that x is nasty, x is a goblin, x is armed, and x is dangerous. Note that I've added a couple parentheses here that help us more closely map the English. What you can see is the atomic formula, right, is such that the main operator there is the conjunction in the middle that's highlighted in yellow, and we get that by using the parentheses. So we can see that that's functioning as the verb to be, as we've said before. That being said, first-order logic doesn't require those extra parentheses. We could just have a straight conjunction without breaking it up, and in which case we're departing a little bit further from the grammar of the English, but that's okay. It means the same thing in first-order logic is the crucial point. Now let's change our example just a little bit. Instead of saying a nasty goblin is armed and dangerous, suppose we say all nasty goblins are armed and dangerous. Now hold on to your seats. These are called universal noun phrases. Can you guess why? Here's another shocker. Universal noun phrases use universal quantifiers. And what you can see is, just as we've said before, the verb to be is translated as arrow when we're talking about universal statements. So this is, for all X, if X is nasty and a goblin, then X is armed and dangerous. Recall that when we looked at the existential statements, the parentheses were optional. That's not the case here. We just won't have a well-formed sentence if we drop the parentheses. We need to know that nasty and goblin are part of the antecedent of that conditional in the atomic formula, and that armed and dangerous are the consequent. Okay, let's wrap up by looking at a few odds and ends when it comes to translating quantified statements. Consider our last example. All nasty goblins are armed and dangerous. Now, one thing you may notice is that there are no goblins, right? Hence, there are no nasty goblins. So here's a question. Is this statement true or false? Well, it may seem surprising. The statement is true. It's what we call a vacuously true universal. So why is this true? If you remember, if we go back to our truth tables for if-then, whenever the antecedent is false, the whole conditional is true. And you can see that that's basically carrying over when we talk about universal statements. Whenever the antecedent of the atomic formula in a universal statement posits non-existent things, the whole universal is going to be true. This may seem counterintuitive. However, let's once again recall some of the distinctions we've made earlier when we've encountered weirdness with first-order logic. This ends up being nice if what you want is a language that's perfectly precise and in particular tailored towards evaluating the validity or invalidity of various inferences. What it won't do is it won't capture how we use universal statements when what we're trying to do is more than that. For instance, when we're trying to communicate in a cooperative manner with our audiences. Right? It's very rarely the case that communicating vacuous universals is useful information for anyone. Right? So for instance, if I were trying to protect my loved ones, I wouldn't be guarding them against nasty goblins, even if it turns out that all nasty goblins are in fact armed and dangerous. Here's another case where first-order logic doesn't give you the complete story of what you're trying to do is be an effective communicator, but it works just fine if you're trying to draw valid inferences. Take existentially quantified statements, such as the example you see here. Some angels are fallen. First-order logic suggests that we should translate this way. There exists an X such that X is an angel and X is fallen. Now, it's very tempting to interpret that this way. Basically, you have your Venn diagrams, you have the set of all fallen things, the set of all angels, and you think that it basically has this sort of structure where part of the set of angels falls into the set of fallen things. And from there, it's very natural to think that in addition to there being some fallen angels, there are also some non-fallen angels as well. And I should stress right here that this is consistent with the claim that some angels are fallen, but what I want to highlight right now is another point. And that other point is this. While it's consistent with the claim that some angels are fallen, that some angels are not fallen, it's not entailed by that statement. In other words, you're making a hasty conclusion if you infer from the fact that some angels are fallen, that some angels are not fallen. Allow me to explain. Imagine that all angels are fallen. Then it would be true that some angels are fallen, but it would not be true that some angels are not fallen. Right? And this is also consistent obviously with the statement that we see here, right? So this is why it's a hasty conclusion to draw that some angels are not fallen. Once again, we need to distinguish first-order logic's primary function, which is to basically tell us whether an argument is valid or invalid, which is why this is good, right? We can actually see some real subtleties in the inferences we can draw from statements such as the one we see here, versus other functions that we want a natural language to perform, such as effective communication. Right? If I know that all angels are fallen, but I only say some angels are falling, I'm withholding information, and so I'm not being a very cooperative communicator with my audience. This is why we typically draw the further inference, but note that that's an implicature, but not a logical consequence of the statement that you see right here.
Thanks, and I'll see you at the next lesson.